This is the application portion for our log and exponential equations. And we're going to start with the first model, a compound interest model. This is the compound interest formula. And we say compound interest because to compound our interest, what that really means is that we are going to reinvest our interest. And our money's going to grow as a consequence of this. And we're going to model this behavior, or at least determine how this works in terms of a total amount after a certain amount of years. So let's go over what this equation involves. I'm going to say here, first of all, you have the initial amount here. Our initial amount is the initial deposit. So in this question, when we read this, number one, compound interest, $1,000 is invested. That's the initial amount, the $1,000. So I'm going to replace that value with 1,000. And then we notice that if we read further, it's invested at an interest rate of 8%. And that's an 8% annual interest rate. So we always use here the decimal representation of 8%, which is 0.08. And this is going to go here. This is our R value. So R is 0.08. And, or before we talk about and, because we're going to have to go in some detail, let's talk a little bit about here. Let's find the color here. Time. The time we're going to invest is 35 years. So our T value here will be 35. That leaves us with the quantity called N here. And N is how our interest is reinvested, how it is compounded. And if I read the question here in part A, it's compounded annually. In part B, it's compounded quarterly, and then monthly, and then finally continuously. So this interest is reinvested. It is compounded by a certain number of interest payments in a year. So let me describe that for you and let you know that N is the number of interest payments in a year. So if your interest is compounded annually, we say N has the value 1. If it's done semi-annually, by the way, it's not asked in this question, but you may see it one day. Semi-annually is actually 2 payments in a year. N is 2. Quarterly, there's 4 payments in a year, every quarter. Monthly, there's 12 payments in a year. Every month you receive an interest payment. And so this interest is essentially reinvested through time. And this is called compounding or compound interest type of model. And in this question, part A, by the way, N is the value 1. So I'm going to replace this N here with a 1. And so our model becomes the following. We get the amount to be 1,000, 1 plus 0.08 over 1, 1 times 35. If I simplify, we get 1 plus 0.08, 1 times 35 is 35. I get 1,000 times 1.08 to the 35th power. And I'm going to write this a little bit clearer because I'm writing at an angle here. It's a little tough. All right, 35 and 35. Well, that's not much, but nevertheless. And at this portion here, what we're going to have to do here is use a calculator. So you guys are going to use a calculator on your homework. and you're going to use order of operation. Let's remember, please excuse my dear Aunt Sally, to actually perform the exponential before you actually multiply by 1,000. So the amount we're going to get here, if we use our calculator now, is going to be 1,000 times 1.08 raised to the 35th power. And I'll write it right here. The amount is 14785.34429. Now, what I discussed in class here was we're going to approximate this to the nearest hundredths. We're approximating to the nearest penny. So our eyeball goes here by the second 4. The arrow goes under the first 4. That 4 says don't change the first 4. So the amount here is approximately $14,785.34. So when we invest $1,000 at 8% annual interest per year, if our interest is compounded annually for 35 years, we get about $14,785.34. Now, I'm going to keep this here. I'm going to notate this next to our problem so we can see the effect. But this is $14,785.34. And that's when our interest is compounded annually. Okay? Now, let's do the same kind of calculation here. And I'm going to do the same work, same calculation, but this time we're going to compound our interest quarterly. Now go back here. That means we get 4 interest payments in a year. So I'm going to have to change this value down here. Change n. Now n is going to be 4. So all of this is going to change here. And let me remove this. And really emphasize the change. This is now 4 times 35, and this is now 0.08 divided by 4. So our formula is going to become same exact model, same procedure. We get 1,000, 1 plus 0.02. 4 times 35 is 140. So this is 1,000 times 1.02 to the 140th power. Now this is an exponential. You're going to use order of operation, so you do the exponent first. That's the base of 1.02 raised to the 140th power. So if I punch this in my calculator, I now get $15,996, and I get 465.98. So we're going to approximate this to the nearest hundredth again, the nearest penny. So I look at the digit to the right of this 6 that's in the hundredths position. Since it's a 5, I add 1 to the 6, and now it becomes a 7. So notice that if our interest is compounded quarterly, that means there's 4 interest payments in a year. The amount now is about $15,996.47. That's when our interest is compounded every quarter. That is 4 interest payments in a year. So the greater the amount of interest payments you compound, or I should say are paid every year, the more or the bigger your money grows. So that's now $15,996.47. Let's get rid of some of these things. Let's try 12 payments in a year. So in this case, n is 12. We get 12 payments in a year. So instead of n being 4, it's now 12. Let's get rid of this. We're going to do all this work all over again. This time, let n be 12. There's a 12 down here. There's a 12 here. I'll get 1,000. 1 plus 0.08 divided by 12 is actually 0.006 with that line. 12 times 35 gives you 420. So if I simplify this a bit, I get 1.0067. I'll get rid of the parentheses here. And that's going to be raised to the 420th power. So let's see what we get. 1,000 times 1.0067 raised to the 420th power. Don't forget that you have an exponential here. I just want to emphasize this a bit. This portion has to really be computed first. It's an exponential before your multiplication, to remind you. And then this amount becomes $16,520.71 if we approximate this to the nearest penny. So you could do this in your calculator. You could look at it and just approximate to the nearest penny. As you can see, when our interest payments are compounded monthly, the amount actually becomes $16,520. So $16,520.71. I believe it's getting a little crowded here. We're going to get rid of it eventually. But as you can see, the greater number of interest payments in a year, in this case 12 interest payments in a year, ultimately after 35 years gives us a bigger amount, a bigger balance through time. And that kind of makes sense because we're planting these kind of interests, the seed, if you want to will. You're planting money and you're getting a more lush sort of amount at the end of 35 years. So that's pretty much a significant difference from annually to monthly. Now, what we're going to work on here is continuous. And as we discussed in class, the number of interest payments on a continuous setting, remember n is the number of interest payments. So to kind of describe this to be paid continuously and remind you that in this case, the number of interest payments, it's almost like saying our interest is actually getting compounded instantaneously. Meaning you get instantaneous interest payments, or we should say you get a continuous interest payment, a continuous reinvestment of our interest. And that's what we're looking at. So the number of interest payments in a year gets arbitrarily big. Now, we have again the continuous interest formula. We discussed how we got this in class. And you get A is A naught E to the RT power is our continuous interest formula, and E is the exponential number. So remember that E is approximately 2.718. It's the exponential number, and this is what we're going to use. Notice again, A naught, this here is where we place our $1,000 investment. So we say, okay, $1,000 goes here. R, the interest payment, the 8%, goes here, and we write it as a decimal. 8% is 0.08. Our time still is 35 years. So we're going to replace this with 35. See what we get. The amount is 1,000 e to the 0.08 times 35. And if I do a simple multiplication of 0.08 times 35, 80% of 35 turns out to be 2.8. So I'm going to punch this in my calculator. And remember, this mimics the idea of interest being paid continuously or instantaneously. Your calculator should have an exponential function key. So I'm going to use this in my calculator. And what I end up getting is that this is about $16,444.65. So this final amount gives you about $444.65 if I invest about $1,000 here. And this is how we handle continuous interest. Question 3. Question 3 is similar in some sense. Now, it is an interest account. It's compound interest. Suppose $25,000 is invested at 6% annual interest, compounded continuously. So we have the following equation to use. So the amount here is some initial amount, e to the RT power. And so we notice that $25,000 is invested, so this is the initial investment. So this value is $25,000. It's invested at 6% annual interest. So R here is the decimal version of 6%, 0.06. It's compounded continuously. And in T years, it'll grow to a particular amount. So they're pretty much telling us that they want us to use this equation. That the amount here is 25,000 e to the 0.06 t. We can write it down here. This is going to model our compound interest. So this is a model that we work with. Now, question A says, how long will it take to accumulate $40,000 in the account? So here's what's going on. Let me stand back a bit and say to you the following. Here's what they want to know. For what time value will my amount A be $40,000? So I'm going to replace my A here. Here's A with 40,000. Now, notice what this gives me. I have an equation that says $40,000 will be our amount for some time t using the model that they gave us or the model that we derived. They want to know for what time t. What we have here, ladies and gentlemen, is an exponential equation. Now, we solved exponential equations on the previous homework. And so if you like, you can rewrite it if you wanted to get your t on one side. You can say 25,000 e to the 0.06t becomes 40,000 and solve for t. Okay, so we discussed this. We're going to solve for the variable t, which represents our time, and we're going to divide by 25,000 to both sides. So we get cancellation. And we end up with e to the 0.06t is the 40,000 over 25,000. We're going to take the natural log of both sides. So natural log of the left equals the natural log on the right. So here's what we get. Natural log e 0.06t becomes natural log of 40,000 over 25,000. Don't forget that we're going to use now the power rule for natural log. That means we're going to pull out this power. Pull this out, okay, by the power rule. And we'll get 0.06t times the natural log of e will still be the natural log of 40,000 over 25,000. Now the natural log of e, if we recall, is 1. So you're going to end up with the equation of 0.06t, again, is still natural log of 40,000 divided by the 25,000. If you divide both sides now by your 0.06, you get cancellation, and now t becomes the natural log of 40,000. Let's kind of write this a little bigger. You get natural log 40,000 over this 25,000 divided by 0.06. And if we use our calculator, we get our time to be, if we approximate this to the nearest tenths, our time is going to be about 7.8 years. So what this means is it's going to take about 7.8 years for our money to grow to $40,000. This is question A. It takes 7.8 years to go from 25,000 to 40,000. If you're paid a 6% annual interest and your interest is compounded continuously. So this is how we actually determine a time value given these other parameters. B is going to say how long, if we look at this, how long will it take for the investment to double? Now what I want to say is that doubling here, let's erase some things and talk about what doubling is going to do. What doubling is, in this case, let's go back and recall that our initial investment here is 25,000. So to double, what doubling is that the amount A is going to be 2 times the initial amount, or the amount A will be 2 times that 25,000. The amount A will become 50,000. So what I'm going to have to do now is replace this A value. That was 40,000, and now replace it with 50,000. So what happens now is this 40,000 gets removed. It is now 50,000. And so we still get, let's change this portion here too. We still get an exponential equation. However, let's look at the details here. $50,000 is the same as 25,000 e to the 0.06t. We're now going to divide both sides by 25,000. 2 is e to the 0.06t. So we're going to do the same mathematics that we originally did. And we get e to the 0.06t is 2. We're going to now take again the natural log of both sides. And we're going to end up with natural log e to the 0.06t is natural log of 2. So we are going to again bring out by the power rule 0.06t. So I have a 0.06t here times the natural log of e is the natural log of 2. Natural log of e is 1. So 0.06t times 1 is the natural log of 2, and we will divide both sides by the 0.06. So our time equation here is going to be t equal to natural log 2 over 0.06. And time now, t here, is going to be approximately 11.6 years. This is our t value. So this will be at 11.6 years. Now, notice something about this equation. As I demonstrated in class, that to double and to find the amount of time it takes to double our money, we did prove here this equation that it's the natural log 2 over your R value in general. So what can happen is you could just change that interest rate, use 8%, use 9%, use 4%, use 2.5%, any R value. Using this equation will give us the amount of time it takes to double. We proved that in lecture. I just wanted to go through it here in a numerical sense, but this is what we do to double. Let's recall that we also worked on how to triple. That's going to be t natural log 3 over r. So the same derivation occurs if we triple. And this is the equation. So if I go back now and say, okay, what are they asking for in question C? Question C is not to triple. If we did want to triple, by the way, we'll call it a by the way, the time will be natural log 3 over that rate of 0.06 for this problem. T would be approximately natural log 3 divided by their R value. This would be 18.3 years. So to let you know, what's happening now is certainly it takes a lot longer. So to triple, it's about 18.3 years versus doubling, which is 11.6 years. So those equations were derived in class, the doubling time, the tripling time. The last question here, question C, is not doubling or tripling. It's how long does it take? Let's read this question. How long will it take for the investment to reach simply 65,000? So this amount again is going to be changed. Let's erase what we don't need. Our A value will become now 65,000. Let's change these. That's 65,000. We now get an exponential equation that looks like the following. So 65,000. So let's take a look here. Here's our equation. 25,000 e to the 0.06 t power is now that 65,000. So we have an exponential equation, and we're going to solve by, again, dividing by that 25,000. Cancellation here, we get e to the 0.06 t is 65,000 out of 25,000. Now, in case you guys didn't know, let's remind you that I can actually get rid of these zeros, and let me write this down. We get e to the 0.06 t does become 65 over 25. Now you might want to figure out why that is. Essentially, it's 65 times 1,000 here on top, right? We get 65 times 1,000 over 25 times that 1,000, and your 1,000 goes away. So that's really what's going on. We're now going to take the natural log of both sides. And our equation becomes the following. We get the natural log e 0.06 t is the natural log of 65 over 25. This value here, 0.06 t, gets removed by the power rule. And don't forget the natural log of e again is 1. So we have 0.06 t is the natural log of 65 over 25. We're getting down kind of low here. Let's get rid of this from the past. Okay. We're now going to divide both sides here by 0.06. It's gone, and t becomes the natural log of 65 over 25 divided by 0.06. Here's what our time's going to be. Let's use our calculator. And it looks like the time's going to be about 15.9 years. So it's going to take about 15.9 years for our money to grow from 25,000 to 60,000. This is the answer now for C. text messaging. So if we read this question, we're saying that in 2000 there were approximately 60,000 text messages. Okay, let's figure this out. 60,000 text messages sent each month through ELAC routers. This number has increased exponentially at an average rate of 16% per year. Determine the following: the exponential growth function that models this data. So the first question is to come up with a function that models this. Now, we do have an exponential growth model format, which is P naught e to the kt power, and k is positive. Again, P naught is the initial amount. So in this question here, if we look at this, let's get the right color. P naught here is your 60,000. So I'm going to actually use 60, but understand that this is actually 60,000. This is measured in thousands. So I can let that initial amount be 60,000. My interest rate is 16%. Now, 16%, let's go back a few seconds here and let's describe things. Let's go back. Okay. Let me remind you that the key here to this is this value here called k. Okay. K here is the exponential growth rate. So k is the exponential growth rate, as we discussed. And in this case here, k is 16%, or k can be described as 0.16. So I'm going to replace this with 0.16. Now the time value t here, let's say this. Your time t is going to be the amount of time after the year 2000. So t is time after year 2000. So what we've done here is pretty much answered question A, that our exponential growth model will say population, or P, is 60 e to the 0.16 t. And this is now going to give me the number of text messages through ELAC's routers after the year 2000. Because question B says the following: estimate the number of text messages sent each month in 2005. So after 2000, if t is the years after 2000, in this question now, t is going to be 5, because to go from 2000 to 2005 takes 5 years. So I'm going to replace this t for 5. Now, this is going to answer question B. So what I'm going to punch in my calculator now is 60 e to the 0.16 times 5. I'm going to say 60 e, 16% of 5, is going to be 0.8. So 60 times e to the 0.8. We get 133.5. 133.5. Now, again, this is also measured in thousands. So about 133.5 thousand text messages now go through ELAC's server. initially it was 60,000. 5 years later, with a 16% growth rate, it's now 133.5 thousand text messages every month. And that's how you answer question B. Question C. How long will it take for text messages to double? Now that's going to 60 to 120,000 really. But again, like we did in the previous problem, let's go over this here. And like we did in class, let's note, to double, again, essentially P is 2 times the P naught. And so if we use this P, this exponential growth model, P is P e to the kt. This portion right here, P and P, we replace with double the initial amount. So I'm going to put that in red and say this is now 2P naught. And the equation you get is 2P naught is P naught e to the kt. And if I divide both sides now by your P naught again, I get cancellation. And we get 2 equal to e to the kt. And when we take now the natural log of both sides, just to let you guys know, we'll write it down. It's a bit messy, so let's not do that. We'll do it this way. Natural log of 2 is natural log of e to the kt. We're here now, by the power rule, we're going to pull this out. We're going to pull out the power. I end up with natural log 2 is kt natural log of e, where the natural log of e is the value 1. Natural log 2 is kt. Divide both sides by k. Here's what we end up with. T again is natural log 2 over that rate k. Just like we did in lecture, just like we noticed in the prior example, k again is the exponential growth rate, and in this case it was 16%, and replace that with 0.16. So the time that it takes to double natural log 2 over this 0.16 now. The time is approximately 4.3 years. So it'll take about 4.3 years. And that's how long it'll take to double. How long would it take to triple? Now, again, look at the next question here. This is D. It's going to be, how long will it take for a text message to triple every month? Well, again, it's just like we derived in class. We described earlier. What's going to change now here for this question is going to be simply this. Instead of doubling, we're going to triple. This is 3. Three. And this here, these values here now are also 3. So I'm going to say here, this is going to be a 3. And that's because to triple, your population now is going to be 3 times the initial population. That's tripling. So I'm going to replace that P with 3P naught. And again, you get this equation we just have to now change this value and find out what natural log 3 is and divide by 16%, and we get 6.9 years. So it's about 6.9 years for the population to triple, or the number of text messages to triple, to go from essentially 60,000 to really 180,000. So this is how we handle the tripling situation. This is an exponential growth model. Cruise ship passengers. In 1980, a cruise line carried 100,000 passengers. The number increased exponentially to 350,000 passengers in 1990. Determine the exponential growth rate and the exponential growth function. So we're going to start with a model that P is P naught e to the kt. Again, k is greater than 0. They want us to determine the exponential growth rate. What they're really saying here for us to do is, what is this value k? So I'll write that down. What's k? And specifically, what's k when what happens? You go from 100,000 passengers to 350,000 passengers. Well, the initial amount here, I'm going to say, we're going to write this way. 100,000 is our initial amount. It's fine blue. 100,000 is our initial amount. That goes right here. So I'm going to put really 100 for 100,000. And at some time, we don't know the time, we go to this value over here. Let's use this. 350,000. Let's use that, sorry. Let's use orange. We're going to go to 350,000. That's going to go over here for our value. And since this is in thousands, I'll use 350. We could do that, or we can actually put the number. 350,000, but make sure this is going to be 100,000. So here's what our model looks like now. 350,000 will equal 100,000 e to the k t. Now again, we have to determine what is t. Let's go back. In 1980, we went from that 100,000. So t here, ladies and gentlemen, let's do this in red. T is the number of years, again, after 1980. Now what that means is, in 1990, which is 10 years later, we're now at the 350,000. So this is what we're going to replace here with our t. T is now 10. So the model becomes 350,000, 100,000 e to the 10t. We have again an exponential equation that we know how to solve. We can divide both sides here at this point with the 100,000. We get cancellation, and this is going to be, if you want to think of it as 350 over 100 again, is e to the 10t, or even 35 over 10 is e to the 10t. Think about how that happens, just like it did before. When we write this with e on the left, e to the 10t, we can now say is about 3.5. Because 35 divided by 10 is 3.5. Take the natural log now of both sides. We're going to pull out the power by the power rule. Pull out that 10t. You'll get the 10t out here. Natural log e is natural log 3.5. Natural log of e is the value 1. 10t is natural log 3.5. Divide both sides by 10, and I'll get t to be natural log 3.5 divided by 10, or t is approximately 1.3. Or sorry, 0.13. Now let's go back and let's think about this. We made a mistake. Here's the issue. This t here is really k. So all along, it wasn't a t value. We made a mistake. That's k. Glad we caught it. So going back and seeing whether this makes sense, that was actually k. Seeing if this makes sense now, k, k, k. This is the rate. K. This is our rate. This is 13%. So k is approximately 13%. That's the growth rate. Now what that means for our model, since k is 13%, we got that here. What that means is, let's erase some of this here. This model is P equals 100,000 e to the 0.13 t. Now, we can also describe this as, really, P equal 100 e to the 0.13 t, where this is measured in thousands. So we can say this is going to give us an answer in thousands. Let's get rid of all this other work. You can always go back in the video. But that was a rate. Solving for t and all these, very easy to make that mistake. This is the rate. They wanted the k value. Okay, what's k? Right, this is what they asked. I erased it, nevertheless. Here we go. So we not only got the value for k, the growth rate, we also got the exponential growth function they asked us for as well. This is what it is. Now, I guess what they're saying here is determine in the next question. Determine the year in which the cruise line will carry 1 million passengers. So I'm reading this. Once I have my equation, I can actually answer the question. Now, be careful. They want to know the time, t, that's the year, right? T is the year after 1980. So I'm going to have to find the value for t here. So if I'm going to use the population now to be, let's erase some of this, 1,000,000. I'm right here. Let's find the color. Let's say orange. I want this to be 1,000,000 now, my population. So how do I represent 1,000,000? In the original, this is 1,000,000. If my model is in thousands, I'm simply going to have to now use 1,000. Because 1,000 times 1,000 is 1,000,000. And my new model becomes 1,000 equals to 100 e to the 0.13t. This is an exponential equation. Solve for t. I can, at this point here, divide both sides by that 100. I get 10 equal to e to the 0.13t. Natural log of both sides. I can now pull out 0.13t. Natural log of e is 1. So our time is going to be 17.7 years here. So it looks like it's going to take 17.7 years at a 13% growth rate. Hold on. It will take this. It'll take 17.7 years at a 13% growth rate to go from 100,000 to 1,000,000 passengers. Now, be careful. They asked us this following question. Determine the year. So let's go back and remember that t is the number of years after 1980. So what we're going to do here is, if we have to determine the year now, 1980 plus the 17.7 years is going to give us essentially, and it depends on how you want to look at this. If you want to approximate our years here to be about 18 to a whole number, the year is very crudely, approximately 1980 plus 18 is 1998. So about 18 years after 1980, we'll go from 100,000 passengers to 1,000,000 with that 13% growth rate. Okay. Half-life. Now, we're going to have an exponential decay model. P is P naught again, e to the minus kt. Here again, k is positive. Now, what that implies, though, is the opposite of k is negative. And then we're going to have to talk about the idea of half-life. Now, in class, we talked about this, half-life. That's the amount of time it's a t-value. It's the amount of time necessary for half of the initial quantity. So the amount of time t for half the initial quantity, that's P naught, to decay. So the key here is this. Half let's go back. We got red. Half the initial quantity called P naught. That means, in red, P is 1/2 P naught. Okay? Now, this is a half-life question. We talked about half-life. What we're going to do here now would be, is for P, this P is going to be replaced now with 1/2 P naught. So we get the equation. 1/2 P naught is P naught E to the minus KT. Cancel your what? P naughts. You're going to get 1/2 equal to E to the minus KT. Natural log of both sides again. Power rule. I'll pull out my power. Natural log of 1/2 is minus KT. Natural log of E. This value is 1. Natural log 1/2 minus KT. Divide both sides by minus K. Cancel. T becomes minus natural log of 1/2 over that K. And if you want to use some properties, we can say this is the amount of time, the half-life time, that's going to give us our half-life. Or we can say that T will be the natural log of 2 over this K value by properties of logs. You see, the minus natural log of 1/2 is natural log of the reciprocal of -1. That's going to give us natural log 2, nevertheless. Okay, we'll write it all down. Let's note. Natural log minus 1/2 is the natural log of 1/2 to the -1 power, natural log of 2. That's where it came from. This is our half-life formula. So if we know K, and K is the decay rate, so let's write this down. Let's change this color, I guess. Call it K. This K here, same K. This is our decay rate. So if you know the decay rate, you can get the half-life very easily. Well, that's what we talked about in class. So in this question here, the exponential decay rate of iodine 131 is 9.6% per day. Now, this here of 9.6% is 0.096. That's the K value. Notice K again is positive. So I'm going to use that value because that's my decay rate. And it says it. The exponential decay rate of iodine 131 is 9.6% per day. What is its half-life? Now the half-life is in a day unit because it's a 9.6% per day rate. So just replace K with 0.096. So this is going to be 0. Let's use the right color. 0.096. That's what this K is going to be. So T will be, let's erase this other work. You know where it comes from. t is going to be the natural log of 2 over 0.096. Use your calculator. Time here, we should say t is approximately 7.2 days. Half-life. Since the rate is in a percent per day, go back here, right? The half-life is also in days because it's the amount of time for half the initial quantity to decay. 7.2 days. That's our answer. Number 11. Number 11. Let's read the question. The half-life of caffeine in the human body is approximately 5 hours. Let's recall that half-life is a time value, and it's the natural log of 2 over k. Okay, we don't have to box it. This is the half-life formula. So when I read the question, what is the exponential decay rate? They're asking us for what is k. Now I know what t is. T is 5, but generally speaking, I can actually solve for k by cross multiplying. K is equal to the natural log of 2 over t. And you say, how did you get that? Well, cross multiply and solve for t. I'll get rid of this. And so if I know the half-life value, and I do, it's 5 hours, I can now find the value for k, the exponential decay rate. Take the natural log of 2 divided by 5. And k is approximately, if I do the calculation, natural log 2 divided by 5, that's approximately 14%, or 0.14. This is the value for k. So that our model now is going to be P equals P naught e to the minus 0.14 t. This is our exponential decay model. Now we need this model because the next question is going to say the following. So let's erase this. How long will it take for 95% of the caffeine consumed to leave our body? Now, how long? How long is the time value? That's t. How long will it take for, and I think we have to read this very careful, 95% of the caffeine to leave the body? Now what that means is if 95% of the caffeine leaves our body, what we have to notice then is that 5% of the caffeine will remain. And that's going to be the key to this question. That if 95% of the caffeine leaves our body, that will mean that 5% remains. So what they're really asking us for is the following. For what t, what time value, will P be 5% of the initial amount? In other words, P will be 0.05 P naught. this is what we're going to replace for this p. This is going to be 5% of the initial amount. So that our equation becomes 0.05 p naught, that's 5% of the initial amount, is the initial amount p naught, e to the minus 0.14 t. We can solve for t. You can divide both sides by p naught or simply cancel it out. We get 0.05 will become e to the minus 14 t. And natural log of 0.05 is natural log e to the minus 14 t. This power by the power rule gets pulled out. And we end up with the natural log of 0.05 equal to minus 0.14 t natural log of e, where the natural log of e is the value 1. So this equation we could write now with t on the left looks like the following. Divide both sides by negative 0.14. Negative 0.14. Here's t. T is negative natural log 0.05 over 0.14. So we need the natural log using our calculator of 0.05. Divide that by 0.14. Don't forget the negative of that. T is approximately 21.4 hours. So in about 21.4 hours, 95% of the caffeine will leave our body. Notice what this means. Caffeine has a half-life of 5 hours. So in 5 hours, half the caffeine will leave our body. But for 95% of it to leave our body, and we'll double check our calculations, natural log 0.05 divided by the 0.14, 21.4 hours later, 95% of that caffeine has left our body. Notice it's not 100%, but 95% of it has left. That's how we answer number 11. Number 13. The half-life of carbon-14 is 5,750 years. Let me emphasize this. Half-life is 5,750 years. So I'm going to write this down. Half-life is a time value. 5,750 years. A date palm seedling is growing in Kibbutz Keturah, Israel, from seed found in King Herod's palace at the Masada. The seed had lost 21% of its carbon-14. How old is the seed? Now let's note that we need our decay rate. So let's first determine the decay rate. So let's recall the decay rate can be found if we say K is the natural log of 2 over the half-life of 5,750 years. So that our decay rate will be approximately natural log of 2 divided by 5,750. So K is approximately 1.20547 times 10 to the minus 4 power. Let's double check. Natural log 2 divided by 5,750 years. Yes. So we're going to have to move the decimal here. 1, 2, oops, 3 spaces. That was weird. 1, 2, 3, 4 spaces. 1, 2, 3 zeros. So we got K going to be approximately 1, 2, 3 zeros. 1, 2, 0, 5, 4, 7. So this is the decimal representation. We're going to have to approximate this. Let's go out to the tenths, 100,000, 10,000ths. This is our decay rate. So our model becomes P equal to P naught E to the 0.0001 t. This is the exponential decay model, and it's minus since it's decay. So we got the decay rate. Boy, that's actually that's less than 1%. That's about, well, 1/100th of a percent. Very small. So once we got the model now, let's see what the question is. The seed has lost 21% of its carbon-14. If you lost 21%, let me write this down in green. What, again, remains? 100 minus 21% is 79%. This is how much remains. 79%. That 79% remains. And that's 79% of the initial amount. So as a decimal, I'm going to replace that with, here, 0.79. Oops, let's go back. That's not what I replaced with. I'm going to replace my P to be 0.79, the initial amount, because this is how much that remains. So as an equation, we have 0.79 P naught is P naught E to the minus 0.0001 t. Again, P naughts go away. We get 0.79 to be E to the minus 0.0001 t. The natural log of 0.79 is the natural log of E to the minus 0.0001 t. Properties of logs. Pull out the power. Here's what you end up with. Natural log of 0.79 is minus 0.0001 t natural log of E, where the natural log of E is the value 1. And so we get negative 0.0001 t natural log of 0.79. Solving for t. Cancel. You can get your t to be negative natural log 0.79 over 0.0001. So t is going to be approximately, if we punch this in, natural log 0.79 divided by 0.12301, and it's negative 2,357.2 years. Approximate this to the whole number, 2,357 years. this is how old I guess this particular seed is. So, carbon-14 has a half-life of 5,750 years. The seed lost 21% of its carbon-14. So how old is a seed? 2,357 years. That's how old the seed is.